Let's dive right into the fundamental physics of motion. Welcome to this explainer. Today, we're taking the seemingly intimidating math behind how things move and breaking it down into a clear, step-by-step journey using everyday examples. I mean, motion is literally happening all around us all the time, right? From massive astronomical objects spinning out in deep space down to something as simple as a ball dropping to the floor. But to truly grasp the complex physics governing our world, we first have to strip it all down to its absolute simplest forms.
So here's our roadmap for today. We're looking at the basics of position, distance versus displacement, speed and velocity, calculating average acceleration, and finally, the kinematic equations. We're going to build our understanding progressively here, starting with simply where you are, moving to how fast you're going, and ending up with the mathematical cheat codes of the universe.
Section 1. The basics of position. Because, well, before we can even talk about moving, we have to establish exactly where we're starting from. To do that, we need a reference point. The absolutely crucial thing to remember here is that motion doesn't actually mean anything without an origin. You need a reference point to measure positive and negative directions from. If you want to know if an object has moved, you have to know precisely where it started at time zero. So whether it's a ball falling straight down or a train cruising on a perfectly straight track like we see here, linear motion, which is just motion in a straight line, is the absolute simplest form of movement we can map out from that reference point. And the moment an object's position changes with respect to that reference point over time, boom, we officially have motion. Moving on to Section 2, distance versus displacement. Now, this is where it gets really interesting, because just covering ground isn't actually the same thing as changing your position. Let's compare these two fundamental concepts, because they get mixed up a lot. Distance is a scalar quantity. That means it only measures magnitude. It tracks every single exhausting step you take, regardless of what direction you're going. But displacement? That's a vector quantity. It measures both magnitude and direction, and it literally only cares about the shortest path between your starting line and your finish line. To brilliantly illustrate this difference, let's look at an example from our source material. We've got a swimmer here named Sarang, and he's swimming laps in a standard 50-meter pool. Let's walk through his 50-second round trip step by step. Step 1. Sarang swims 50 meters from one end of the pool to the other. Step 2. He turns right around and swims 50 meters all the way back to his exact starting point. Step 3. Let's calculate the net change in his overall position. Now, if we're asking for his total physical distance covered, that's easy. We just add 50 plus 50 to get 100 meters. But to find his displacement, remember, we only compare his final position to his starting reference point. And because he ended up exactly where he started, his total displacement is a surprising 0 meters. Think about that. All that physical effort, 100 meters of actual distance traveled, but mathematically, 0 displacement. Section 3, speed and velocity. Let's add the next layer to our journey and see how bringing time into the mix completely changes our understanding of pace. So average velocity is the net change in position, which, as we just learned, is called displacement, divided by the time interval during which it occurs. Well, average speed just tells us how fast physical distance is being covered. Average velocity calculates how fast the actual position is changing. It effectively brings direction into the math. You can think of it kind of like a compass. Velocity requires a direction. For straight line motion, we usually indicate this with a plus or minus sign. This means you could literally be traveling at a super high speed but have 0 average velocity if your net displacement is 0. Going back to Sarang's pool example, since his displacement was 0 over those 50 seconds, his average velocity was exactly 0 meters per second, even though his average speed was actually 2 meters per second. Let's scale that up. Imagine a family road trip. You drive 200 kilometers north in 3 hours, and then you immediately turn around and drive 200 kilometers south in 2 hours. That's a massive total distance of 400 kilometers, right? Divided by 5 total hours, that gives you a totally respectable average speed of 80 kilometers per hour. But because you ended up pulling into the exact same driveway you started from, your net displacement is 0. 0 divided by 5 hours means your overall average velocity for the entire trip is exactly 0. Pretty wild, right? Section 4. Calculating average acceleration. Okay, let's dive into what happens when that nice, steady velocity suddenly shifts. Average acceleration is the change in the velocity of an object divided by the time interval over which that change actually happens. So acceleration isn't just about moving fast. It's specifically the rate of change in your velocity. You know exactly what this feels like. It's that sudden physical jolt you feel in your seat when a car slams on the gas from a standstill, or when it suddenly aggressively stops. Picture this. A bus driver is cruising along at a constant high speed on a straight highway. Suddenly, they spotted an obstacle on the road ahead and have to just slam on the brakes. Let's calculate this exact scenario step by step using an example from our text. Step 1. Identify the initial velocity before the braking starts. Let's say the bus is traveling at 54 kilometers per hour. For our math, that conveniently converts to 15 meters per second. Step 2. Note the final velocity. The bus comes to a complete, screeching halt, so the final velocity is 0 meters per second. Step 3. We divide that change in velocity by the braking interval. Let's call it 5 seconds. The change in velocity is always the final minus the initial, so 0 minus 15 gives us negative 15. Then we divide that negative 15 by those 5 extremely stressful seconds. And that calculation perfectly captures deceleration. We get negative 3 meters per second squared. That negative sign is crucial. It tells us the acceleration is acting in the exact opposite direction of the bus's forward velocity. That invisible force, that negative acceleration, is quite literally what forces your body forward when the brakes lock up. Section 5. The kinematic equations. Now that we've mapped out position, displacement, velocity, and acceleration, it's time to tie the whole shebang together. Take a look at these. These are the 3 kinematic equations. They are basically the mathematical engines that connect displacement, time, initial velocity, final velocity, and constant acceleration. The beautiful part? If you know any 3 of these variables for an object moving in a straight line, you can use these exact formulas to calculate the missing pieces. Seriously, don't think of these as just dry, boring math problems. Think of them as predictive cheat codes for reality. If you know an object's starting conditions, like its initial velocity and exactly how fast it's accelerating, you can perfectly calculate its exact future position or its future velocity. You just take the numbers you have, plug them into the right equation, and out pops the variable you're missing. It's almost like magic. So I want to leave you with this somewhat provocative thought. If mastering these 3 basic equations allows us to perfectly, accurately predict the future position of a moving car or a falling ball, what else in the universe is just waiting for you to predict it? It kind of makes you realize that the world around us isn't just chaotic randomness. It's perfectly structured, and it's just waiting for you to learn the right formulas. Thank you so much for joining me for this explainer. Keep asking those big questions and keep learning.